Today on AI Paper Podcast, we are breaking down Omni-R1 towards the unified generative paradigm for multimodal reasoning by Danji Cheng, Youngki Lee, and a whole team of colleagues.
And this one proposes a really fundamental shift for multimodal large language models. Instead of just looking at an image and then thinking in text, this paper introduces what they call unified generative multimodal reasoning.
Which means what exactly?
It means the model actually generates intermediate images to help it think. It's a visual chain of thought. It can zoom in, draw bounding boxes, even add lines to a geometry problem to solve it.
So they've got two main frameworks. There's Omni-R1, which is supervised, but the really big deal is Omni-R1 0. This one bootstraps all those visual reasoning skills using only text data. No expensive hand-labeled multimodal data needed.
Right, and that's the main takeaway. The zero version, the self-taught one, often matches or even beats the fully supervised model. It proves MLLMs can kind of teach themselves how to see and manipulate images to reason, which could break the biggest data bottleneck we have in this space.
Welcome back to AI Paper Podcasts. We're going deep today. This paper is a beast, and if you're building MLLMs, honestly, this is probably required reading for the month. We're moving from a model that just looks at a picture to one that actively works on it.
It's a necessary step, you know. You look at GPT-4v, Gemini, LLVA, they all kind of share this one limitation. They see an image once, encode it, and then the whole reasoning process is just text, purely textual.
Right. It's like looking at a complex diagram, closing your eyes, and then trying to solve it from memory.
Exactly. And look, for simple stuff like what's in this picture, that's fine. But for really complex reasoning like geometry problems or planning a robot's moves or even deep document analysis, it just falls apart.
Because it can't, lean in closer or grab a pencil and sketch on it.
It can't. And this paper, Omni-R1, is all about building a system that can literally modify its own visual input to figure out the answer.
They call it UGMR, Unified Generative Multimodal Reasoning. Before we dive into the architecture, which had some really clever loss functions, let's just nail down what the model is actually doing. These Unischool they talk about.
Right. These are like the building blocks of visual thought. The paper breaks it down into 5 core skills. First, you've got zoom in, pretty straightforward. The model generates a new, cropped, higher res image of a specific spot.
Okay.
Then you have BBOX grounding, so drawing boxes, and marking, which I think is super important for stuff like counting. It literally writes numbers on top of the objects in the image.
I want to pause on the 4th one because this one blew my mind a little. Drawing a line.
Yeah.
They show this geometry problem, and the model generates a new version of the image where it has drawn a red dotted line to help it solve the proof.
That's classic system 2 thinking, right? It's deliberate. That line didn't exist in the input pixels. The model had to, in a very controlled way, hallucinate it to make the math possible.
And the 5th skill, which I'm sure a lot of our listeners in robotics will care about, is visual prediction.
Yeah, this is where it goes from static to temporal. You give it a prompt, like move the block to the left, and the model generates the next frame. It predicts what the scene will look like after the action. It's running a little physics simulation in its head.
Okay, so that's the what. Let's get into the how. How do you train a model to draw useful things on an image without it just, hallucinating complete nonsense? Image generators are not known for their restraint.
That's the core engineering problem here. And they tackle it with a 2-stage process. The first stage is called PeSFT. That's Perception-Aligned Supervised Fine-Tuning.
So standard SFT is just predicting the next token with cross-entropy loss.
Right, but the problem is your next token might be an image. If you just use a standard loss, the model could generate a beautiful image that has nothing to do with the original, so they add this perception alignment loss.
And what's that doing mathematically?
Without getting totally lost in the equations, it basically acts as an anchor. It forces the features of the generated image patch to stay very close to the features of the original image. It says, sure, you can draw a box, but the pixels inside that box have to match what was there before.
So it stops the model from deciding a zoomed-in picture of the Toyota should suddenly become a Lamborghini.
Exactly. But, SFT is just imitation. It teaches the model the format of how to reason visually. It doesn't teach it to reason. For that, they need reinforcement learning. Stage 2. PeRPO, Perception-Calibrated Relative Policy Optimization.
RL in multimodal models is always so tricky. The reward is usually just like, yes or no, did you get it right? Super sparse.
And they fix that. They make the reward much richer. It's split into an accuracy reward and a format reward, but the key, the real innovation, is that perception-calibrated part. The RL algorithm gives a bigger reward if the visual evidence it generated was the reason it got the right answer.
So wait, If the model guesses the right answer, but it drew its bounding box on the completely wrong object.
It gets penalized.
Ah, okay.
It forces a causal link. You have to see it correctly to get credit for answering it correctly. It stops the model from just learning to ignore the image and guess from the text.
Okay, so that's Omni-R1, the supervised model. But this brings us to the massive elephant in the room, the data. To train this, you need interleaved data. Text, then an image, then more text.
Which just doesn't exist, not at any real scale.
Right. I mean, can you imagine the cost of paying people to sit there with Photoshop, drawing boxes and zooming in on images for millions of examples? It's completely unscalable.
It's the biggest wall in the field right now. And that's exactly why Omni-R1 is the real headline here. They found a way around it. They don't need any human multimodal annotations.
This is the bootstrapping process.
Yeah.
So how do you get visual reasoning data from nothing?
Well, not from nothing. You get it from text. We have enormous data sets of text-only chain of thought reasoning. Models explaining step by step. First, I need to look at the car's wheel. Then I need to check the logo on the hubcap.
Okay, so you got the script of the thought process. You've got the script. And they use this method, bootstrapping stepwise visualization. They go through that text chain, and every time the model says it's looking at something, they prompt the image generator to create the corresponding visual.
So you're forcing the model to draw a picture of its own internal monologue.
Precisely. It synthesizes its own interleaved data. Text says, I need to focus on the license plate. The model is then forced to generate an action, a zoomed-in image of the license plate.
But hold on, if the model isn't fully trained yet, aren't those generated images going to be kind of bad?
They're noisy, for sure, but they're grounded enough from pre-training to act as a weak supervisor. They generate thousands of these synthetic reasoning chains, filter out the really bad ones, and then they just run the same PeSFT and PeRPO training pipeline on this data it made for itself.
It's basically writing its own textbook and then studying from it.
And the big question becomes, does the student who wrote their own textbook learn better than the student who was just handed the teacher's notes? Let's look at the benchmarks then. They built this thing called OmniBench. What does it cover?
It's pretty comprehensive. 4 big domains: natural scene perception, structured images like charts and tables, diagrammatic math, so geometry, and vision operational scenes, which is the robotics stuff.
And the big reveal.
Yeah.
How did the zero-shot model do against the supervised one?
On average, Omni-R1, the self-taught one, matches or even outperforms the fully supervised Omni-R1.
That's wild. The model trained on messy synthetic data beat the one trained on clean, human-annotated data.
And on some tasks, the gap was huge. In the vision operational tasks, the robotics planning, Omni-R1 was way ahead.
Why? I mean, why would synthetic data be better?
The authors have a theory. It's about diversity. Human annotators are, well, we're predictable. We solve problems in standard canonical ways. We draw nice, neat boxes.
Right.
When the model is bootstrapping itself, it explores all these unnatural visual aids, weird crops, strange ways of highlighting things, stuff a human would never do. But that might actually provide more information for the model's specific architecture.
That reminds me of the TSNE analysis in the paper. I was looking at those plots. They're visualizations of the data clusters.
It's such a striking figure. The supervised Omni-R1, the one trained on human data, its clusters are really tight and compact. It learned to perfectly mimic how humans do it.
Coloring inside the lines.
Totally. But the Omni-R1 clusters, they were all over the place, super dispersed. It was exploring a much, much larger part of the solution space.
It was exploring the weird but effective parts of the map.
Exactly. And it suggests that maybe our human intuition about how to visualize a problem, it might actually be a bottleneck.
I want to circle back to the evaluation for a second, the verifier. When you're doing RL, you need to know if the answer is right. But in math, 45 and 45.0 are the same answer, but they're different strings.
Yeah.
That can mess up your reward signal.
Oh, it's a huge pain point in this kind of research. A simple string match is too brittle. It kills learning. So the authors use what they call prioritized matching. It's a hierarchy of checks.
Walk me through it.
First, it tries a numeric match. Does the float value equal the other float value? If not, it tries a symbolic match. Does this latex expression simplify to the same thing as the other one? And only if that fails does it fall back to more conservative text matching.
That makes sense.
It's just a much more robust way to give the reward, and without it, that PeRPO stage probably would have failed.
So we talked about the examples, the geometry line, but the robotics one, the vision prediction, that feels like the killer app.
Absolutely. The prompt is simple. Put the carrot on the plate, and the model spits out 4 frames, Frame 1, gripper moves toward carrot. Frame 2, it grabs it. 3, it moves over the plate. 4, it releases.
What's so amazing is that it's not just planning the motion, it's hallucinating the physics. It has to know that when the gripper opens, the carrot falls down.
And it knows that because the underlying image generator was pre-trained on billions of images where gravity was a thing. The reasoning model is basically unlocking that latent physics knowledge from the vision model to check its work.
It's using the image generator as its own little physics engine.
Precisely.
Okay, let's talk about the ablation studies. What happens if you start breaking the model? What if you just take out the RL stage, the PeRPO?
Performance tanks, especially on the hard multi-step problems. SFT alone is good enough to teach it zoom in on the cat. It's not good enough for zoom in, read the number, then use that number in an equation. You need that reward signal to chain the steps together.
And what if you remove the perception alignment loss? If you just let the generator draw whatever it feels like?
It becomes totally unstable. The model collapses. You have to remember, a model like Stable Diffusion is trained to make pretty pictures. Aesthetically pleasing pictures. It does not want to make an ugly photo of a car with a big green box and floating red numbers on it. That's out of its training distribution.
So the alignment loss basically forces the model to be ugly but useful.
That is a perfect way to put it. It optimizes for functional utility over aesthetic coherence.
So synthesizing all this, the final thought for me is still that point about the synthetic data. The idea that the model found a better way to see than we could teach it.
It really suggests that as we build more powerful models, we might need to stop trying to force them to think like humans. If we let them design their own internal tools, let them draw their own weird, non-human scribbles, they might end up understanding the world in a way that's, well, just better.
Our own intuition could be the training wheels, and at some point, you have to take them off.
In this case, it looks like it was. The model rode faster without them.
That's a hell of a thought to end on. For anyone listening, if you want to see what these ugly but useful images actually look like, go check out the paper. The visualizations are worth it. Thanks for listening to the AI Paper Podcast.
We'll see you next time.